Hey everyone! So in this video I'm going to make a compilation of my previous videos on agentic design patterns. So if you have watched those before, then this will feel really familiar because it's basically a compilation. The reason why I've done this video is that I thought it would make sense to combine my 4 lessons about agentic design patterns into one single course, because I've seen that there's a lot of traction, a lot of interest in the ML community about this series of videos. So I thought, okay, we could make some kind of comprehensive open source free course. So that's the reason behind this video. Okay. And for those of you who are new to the neural maze and to my content, just to let you know that I believe this course is a very good way to get started in agentic AI. The reason is that we are not going to rely on any framework. We are basically going to implement from scratch, just using Python and Groq as the LLM provider. We are going to implement from scratch the 4 agentic patterns. That is, we are going to implement the reflection pattern, a reflection agent. We are going to implement tools and the tool decorator, and also a tool agent. We are going to implement the React pattern. This is the most commonly used pattern out there. And we are going to implement, of course, a React agent. And finally, we are going to implement a MultiAgent framework ourselves from scratch that is going to work pretty similar to Crew AI and also to Apache Airflow. And yeah, that's basically what we are going to build throughout this course. It's structured, as I was saying, in 4 modules. The first module is going to be about the reflection pattern, the second about tools, the third about the planning pattern, and the fourth one about the multi-agent pattern. Alright, so I think that's everything for this quick introduction. Let me know what you think in the comments of this video, and I also drop a link to my Substack blog where I have created complementary lessons to each one of these modules or videos, where I'm explaining with written words what I'm trying to explain here in the videos. And you will also have code snippets, etc. And of course, you will also have the GitHub repository if you want to check it out. All right, so yeah, that's everything. Let me know what you think. And also let me know if you are interested in any additional topic for me to cover in this YouTube channel. But yeah, happy learning, and I hope you enjoy this course. See you on the other side. So yeah, I'm going to show you the project that I've been working on for the last couple of days. It's called Agentic Patterns, and it's from scratch implementation of the 4 agentic patterns as defined by deeplearning.ai. If you go to the README in the repository, which by the way I'm going to leave in the description of the video, you will see that there are 4 agentic patterns: the reflection pattern, the tool use pattern, the planning pattern, and the multi-agent pattern. Today we are going to start with the reflection pattern. We are going to implement from scratch this pattern, but in the next videos, because this is going to be a video series, in the next videos we are going to implement the remaining patterns. That is the tool use, the planning, and the multi-agent pattern. Let me explain to you very simply what's the basics of this reflection pattern. So as we were saying, in today's video we are going to focus on this pattern right here, the reflection pattern, which is the most basic, but at the same time the results are quite interesting in terms of the LLM results. So this diagram showcases the inner loop that we are going to find in this reflection pattern. So you can see there are 2 main blocks: the generate block right here and the reflect block. And what we are going to do, the workflow of this pattern is the following. So suppose the user provides a prompt, like for example, generate an essay about something, let's say Vivaldi, for example, the composer. Okay, so this is the user prompt, all right? This user prompt is going to be received by the LLM. In this case, I'm going to use Groq. But yeah, this block is going to receive this prompt,
And what it's going to do is basically generate an essay about Vivaldi. I mean, this is like a very zero-shot prompting style. It's really simple. And the essay is this text file that you can see right here. This icon portrays the result of this generate block. After that, the result is going to be sent into the reflect block. And this reflect block is going to provide some critique, some feedback to the generate block. You can see in here, this icon right here, where the LLM is going to provide some suggestions, some modifications, etc. to the original content. After that, the result of this critique is going to be sent again to the generate block. And now the generate block is going to generate another version of the TXT of this essay, but taking into consideration all the critique, all the feedback that the reflect block sent to it. Okay, so now it's going to generate a V2 of this TXT. Okay, and the loop will continue over and over. Generally, you can stop the loop with using two ways. The first way is to use an n number of steps, like for example, keep iterating for 10 steps and then stop the loop. And another way is to define some stop keywords. Like for example, suppose that in the reflect block, we say that in the system prompt of this LLM, we could say something like, when you think that the result or the essay, the essay about Vivaldi is good enough, you can generate this string, this stop string, for example, or you can generate something like OK. And when during the iteration we receive any of these stop strings, we will stop the iteration basically, and the loop will finish. Okay, so I know this is very theoretical, but I want you to really understand the inner workings of this pattern, because I mean, you can possibly apply this simple pattern to many of your LLM calls, and I can assure you that it will probably improve the results by a lot. Okay, so now that we have all of this covered, all the theory covered, I think it's time to go to the code. So the first thing you will need to do is to simply clone this repository, and we will be working with two main folders. The first folder, well, let me show you in VS Code. So the first folder that you're going to work with is the notebooks folder. This notebooks contains just the reflection pattern at this time, but as time goes by, you will see more notebooks inside this folder as I continue to develop this project. And then we will also work with this folder in here, the reflection pattern folder inside this directory, which contains like a proper implementation in Python. But we will start with the notebook, where I will give you some easy to understand implementation of this pattern. And after that, we will move into the Python implementation. Right. So once you have the repository installed, you can simply start Jupyter Lab or Jupyter Notebook and work with me in this notebook. So the reflection pattern, as we said before, is a pattern that allows the LLM to reflect and critique its outputs. As you can see, we are using the same diagram for the reflection pattern. And it follows the next steps that we already know. So the LLM, the first step, the LLM generates a candidate output. The second step, which is this 3-step here in the diagram, the LLM reflects on the previous output. And finally, the LLM modifies the original output based on the reflections, and another iteration begins. So we already know that. So now it's time to implement. Okay, so we will start with the first generation step, like an easy to go implementation of this step, so that you can really appreciate the way that the output is going to be refined and is going to be improved in the different steps. So in this generation step, we are going to ask the LLM to generate an implementation of a very common, a very famous sorting algorithm, which is called the merge sort. Okay, We'll be using Groq, as I told you before, and in particular, we will use the Llama 3 70 billion model. Okay, so let's import the relevant packages and clients. In this case, the important one is the client. Okay, by the way, you can see here that I'm loading all the environment variables. Let me remind you that you will need the Groq API key. I'm not going to get into the .env, but as you can imagine, you will need a Groq API key defined in this environment variables file for everything to work. Okay, so let's begin then, and let's generate a system prompt. In this case, we are going to tell the generate block to behave as a Python programmer tasked with generating high quality Python code. Your task is to generate the best content possible for the user's request. If the user provides critique, respond with a revised version of your previous attempt. Okay, so this is going to be the system prompt for this block over here. Okay, for the generate block. Right, now we are going to continue and we are going to add another prompt, in this case a user prompt, into the generation chat history, into the history of messages for the generate block. And in this case, the content is going to be the user content. Generate a Python implementation of the merge sort algorithm. Okay, so finally, we are just going to generate the Python implementation, and we are going to append the result as an assistant role, because this is the response from the LLM, to the chat history as well. Okay. Now simply display the markdown to see the first step that we are going to find. So as you can see, here's a Python implementation of the merge sort algorithm, and you can see that it makes sense, more or less. Yeah, I think so. Yeah, it makes sense. We have two functions defined, the merge sort function and also the merge function. And we have some example usage, which is really cool as well. Now let's get into the reflection step. As you remember that the reflection step is in here, and it will reflect on the code generated by the previous step. Okay, it will reflect, it will provide feedback to this step, to this content, to this content in here. Okay, as you can see, there's a picture of Andrej Karpathy. I thought it would be funny for the LLM to behave as Andrej Karpathy when it provides feedback to the generate block. So that's what I did. As you can see, the content, the system prompt for this block, for the generation block, states that you are Andrej Karpathy, an experienced computer scientist, and you are tasked with generating critique and recommendations for the user's code. So we are going to put the system prompt into the reflection chat history. Just notice in here that we have to use two different histories, one for the generation block and another for the reflection block, which are represented by two Python lists, by the way. So now let's put the reflection chat history and let's generate a critique to the Python code. Let's generate this feedback. Okay, so let's see what Karpathy has to say. Okay, as you can see, there are a lot of things in here. So code organization and comments, your code is well organized, blah, blah, blah. But consider adding a blank line between the function signature. Okay, some minor details, naming conventions, which is a good remark, recursion, merge function, some complaints about performance, the example usage, which seems to be okay. Yeah, but it says that we should add more test cases to demonstrate the robustness of your implementation, which sounds sensible. And yeah, a minor nitpicks. And here we have a very beautiful implementation or revised implementation of the same function. As you can see, there are some doc strings and yeah, doc strings in the two functions, and as well like some sample usage. This is the previous one, I think, and more additional test cases. Okay, so now let's add this system prompt into the generation chat history. And as you can see, we have ended the first step. Okay, this first step. And now we will start again in here. We will start again another step where the generation block is going to use the feedback provided by the reflection block. So that's really easy to do. We just need to pass the updated generation chat history into the generation block and simply display the result. Okay, so as you can see, the generation block has generated some revised code. It implements the merge sort again, but with docstrings, and the merge again with docstrings, and it provides some additional tests and example usage. And now the iteration will continue. I mean, we could create another section in a notebook where we will generate another generation step 2, where we will reflect on the output from the generation block once again, but the loop will continue over and over. So what I did is to implement a Python class that reflects in a much better way this reflection pattern. And as you can see here, we are importing this reflection agent from the library from agentic patterns. This is really easy to do. I mean, you just need to go to VS Code or to PyCharm and install the package using Poetry. In this case, I'm using Poetry for all the dependency management and all the packaging of the Python package. And once this is installed, you will be able to access the classes that I will be defining. But let me show you the class that I implemented for this. It's called the reflection agent, as we saw, and it's really easy to understand, I think, at least, but you can leave me your impressions in the comments. But it just defines one generate method that simply generates the code, the merge sort code, if we keep using the example. And then it also implements a reflect method, which reflects on the generation by generating a critique or feedback for the generation block, as we saw in the notebook. But this is like a proper implementation in Python. It also uses some colorama, as you will see, to create beautiful logging colors when we print the outputs. I think it's I think it improves like the readability of the logging. And finally, the run method, which is the main entry point of this class, where you will pass the generation system prompt, as we defined in the notebook, the reflection system prompt, a user prompt, the maximum number of steps for the iteration to run, and a verbosity level. And it will basically implement everything that we have defined in the notebook. So it will generate the generation history list and also the reflection history list, and it will start iterating over the number of steps. This fancy step tracker is just a helper tool for all the colorama stuff for printing visuals, and then we will generate the output based on generation history. We will update the histories, and we will reflect and critique the generation, and the loop will keep going and going until the iteration stops. Okay, so let's see this in action. Let's simply import the reflection agent from agentic patterns. Let's instantiate the agent, and let's define the basic prompts that we have defined previously, but let's redefine them for clarity. So first of all, the generation system prompt, we just copy and pasted the previous prompt. Then the reflection system prompt, we just copy and paste it again. And finally, the prompt or the user prompt, if you want to be more precise on the naming, which is the Python implementation of the merge sort algorithm. And now we're just going to run this agent. Okay, and as you will see, it's going to start iterating over the different steps. So first step, generation block. This is the output of the generation block in blue. Then the reflection, output of the reflection block in green, and we keep going. So second step, and we generate the Python code again with all the feedback provided by the reflection block, and we keep going and going and going. And here we have the final result. This is the last generation. You can think of it as the best generation so far before we stopped the loop at the 3 steps. And yeah, you can see that the LLM is responding to the reflection block by saying that it's going to incorporate some brief explanation of merge sort, which I guess it's incorporated here in the docstring. It's also adding the time complexity, space complexity, etc. And it's creating, as you can see here, this main function when it's going to put this example usage, and also calling the main function directly from here. So today we're going to move into the second pattern, that is the tool pattern. And before we begin, I'm pretty sure that you're already familiar with this pattern in a practical sense. What I mean by this is that you have probably used in the past tools in LangChain, in Llama Index, or in Crew AI. And the thing is that in today's video, I'm not going to teach you how to use these tools in specific frameworks. I'm just going to teach you how these tools work under the hood. And I think that's really insightful, because if we really understand how things work under the hood, I think it's much easier for us to learn how to apply them in the proper way. So, as we did in the previous video, we are going to start with a Jupyter notebook that covers all the theory step by step, and then I will move into VS Code, where I will show you all the abstractions and all the classes that I have implemented to make this tool more robust, to try to mimic the structure that all of these frameworks offer at this moment. You know, having like a tool class and a tool agent class, very similar to what we did with the reflection pattern, but with the tool pattern. Okay, so let's begin with the theory of the tool pattern. You have this diagram right here that tries to offer a simplified description of what the pattern does or tries to implement under the hood. But basically, let's start by defining what is a tool. And a tool, let's put it in simple terms, it's just a way for the LLM to access the outside world. And what do I mean by this? Remember that LLMs store all the information in their weights. So when you ask an LLM about specific information, that information is going to be retrieved by the weights. But sometimes the information stored in these weights is not enough, and we need a way for the LLM to access the outside world. And that's exactly what a tool does. A tool is just like a Python function that the LLM can access and run and fetch some relevant results using an API or parsing web content or consulting Wolfram Alpha to calculate some difficult integrals. But you get the point. It's a way for the LLM to get outside the information stored in its weights. Okay, so let's start by defining a simple Python function. You have it in here. So this Python function, which I'm a bit ashamed of it because it's too simple, basically gets the current weather. And as you can see, if location is Madrid, it's going to return a temperature of 25. It varies on the unit that you want to put, but given that it's Madrid, it will be unit Celsius, so it's going to return a temperature of 25 degrees Celsius, and otherwise it's going to return 58. So as you can see, don't pay too much attention to this function because it's trivial, but it will help us to illustrate how a tool works. So if we run this, as I was saying, if we run this function with location Madrid and unit Celsius, it's going to return this dictionary, well, this string containing a dictionary with temperature 25 and unit Celsius. So nothing to add about this thing. This is trivial. Okay, so let's proceed. Now the question is, how can we make this function available to an LLM? Because as you already know, LLMs are just NLP systems, and natural language processing systems. So they expect text as input. But we need a way to for the LLM to really understand that this is a Python function, and I can call this Python function to retrieve some relevant results. And how can we do that? Okay, so what I propose here is to use this system prompt. So as you can see in this system prompt, we are telling the LLM to behave as a function called an AI model. We are going to provide the function signatures within these XML tags, these tools tags. And you may call one or more functions to assist with the user query. Don't make assumptions about values, blah, blah, blah. Okay, but the important thing is that we are going to pass all the relevant information within these XML tags. And the LLM is going to return the function call inside these XML tags. Okay, this tool underscore tag, underscore call, sorry. You can see here an example of how we expect the LLM to return the tool call. It's going to be something like this. We are going to, the LLM is going to provide a name, the name of the function, and also the arguments that we need to use to retrieve the relevant information with this Python function. And then a list of the available tools. In this case, I'm just using this one, like get current weather, because I needed to hard code everything for this tiny example. But as you will see in the VS Code, we are going to make it automatic. So given a Python function, we are going to retrieve all of this information, all of this function signature. It's going to be retrieved automatically in the VS Code implementation. But yeah, if you checked the information that we are providing for each tool, you can see that we are providing the name of the tool, a description. This is something that we can get from the docstring, by the way. We will see that later. But yeah, like get the current weather in a given location, blah, blah, blah. And then the parameters, where we are putting all the different parameters. And this is really important, the type of these parameters. In this case, both the location and the unit are going to be strings. But suppose that we are passing, I don't know, the month, and we want it to behave like an integer, then we should put that type inside the function signature. Okay, so now that we know how this system prompt works, let's put it into practice. Just a quick reminder, today we are going to use a different LLM than the previous video. In the previous video we were using Llama 3 70 billion, but today we are going to use a slightly different LLM because it's the Llama 3 70 billion tool use. So it's a version of Llama 3 that's been fine-tuned for tool use. And that's exactly what we want to do today, so it made sense to use this LLM. Okay, we defined a constant system prompt where we copy and paste the system prompt that I shared with you right in the cell below. And now let's run this cell. We are going to ask the LLM what's the current temperature in Madrid in Celsius. We're going to add the system prompt, and we are also going to add the user message to the history. And yeah, let's run this. Okay, so as you can see, we are having a structure similar to the one we ask for the LLM to return in the system prompt. The LLM is returning the name of the tool, and it's also returning the arguments. Since we ask what's the current temperature in Madrid in Celsius, the arguments is going to be Madrid as the location and Celsius as the unit. Okay, but now this is not usable by the LLM. I mean, we have a string, and inside that string we have this dictionary inside these two XML tags. So we need a way to get rid of the XML tags and also transform this dictionary, this string dictionary, into a proper dictionary using the JSON package, the JSON library. Okay, and that's exactly what this function does. This function will get rid of the tool call, or to be more specific, it will get the code inside the tool call XML tags, and then it will transform that string dictionary into a proper dictionary. So let me show you how it works. But as you can see, when we call this parse tool call string, this method, to the output remember that it's this one here, it's going to return a proper Python dictionary. And now if we run the getCurrentWeather, the function that we defined at the beginning of the notebook, if we run this function with the parameters that we have just parsed, it will return the result. So temperature 25 and unit is going to be Celsius. Okay, without any information about the XML tags. That's something that we want to get rid of. Nice. Okay, so now we have the result. As you can see, it's this Python dictionary right here, but we are not over because we don't want the LLM to respond with this structure. I mean, if I ask the LLM for the current temperature in Madrid, I expect the LLM to respond me something like, the current temperature in Madrid is 25 degrees Celsius, for example, but not something like this, not this dictionary. So the last thing that we need to do is to add this observation, the dictionary here, to the chat history. Okay, and we are going to add this into the prompt, this observation, the observation text into the prompt, and finally just call the agent. And as you can see, the result is exactly what we expected. So the current temperature in Madrid is 25 degrees Celsius. Okay, so now this is everything for this dynamic or step-by-step way of doing things, but as you might imagine, this is not scalable. I mean, we can't generate this function signature for everything that we are going to build. I mean, we could, but it's not going to be efficient. We need a way for the agent to, given a Python function, being able to extract the function signature. By signature, I mean this type of structure right here, and also to decide between different tools. So instead of doing all of this process, we need the agent to extract all of this logic away from the user and to do it under the hood. And that's exactly what we are going to do right now, the logic that I'm going to show you in VS Code, how to implement all of this the proper way. So let's get into VS Code. Okay, so here we are in VS Code. Let me show you the new modules that I have added to the repository. So if you go to the source agentic patterns folder, you will find a new folder, the tool pattern folder. And inside you have three modules, the tool agent, the tool, and the utils. Let's begin with the tool, because I think it's the most important topic of today's video, and the tool agent at the end of the day is just a way to interact with the tool. Okay, so this module starts by implementing a method that allows you to get the signature out of a Python function. So this is basically the method I'm referring to. It receives as parameter a function, and it will get the schema, and out of the schema also the function signature. And the function signature, it's basically the structure that we defined on the system prompt previously. All right. Next, we have this class right here, tool class, that has three attributes: a name, the function, and the function signature. The function signature, as you might imagine, it's going to be generated by this function right here. And the function, it's basically the function that we want to call. When the LLM decides that it wants to use a specific tool, this function is the Python function that's going to be used under the hood. And then we have this tool decorator that can be used to decorate your Python function and to automatically transform the Python function into a tool object. If you inspect a little bit the implementation of this decorator, first you can see that it generates the function signature out of the get function signature method that we explained before, and then it returns a tool object by defining the name using the function signature, passing the function that you are decorating as the function attribute that the tool expects, and finally getting the function signature from the variable that we defined previously. Because remember that we were getting the function signature using this method, and having these three attributes, we are able to generate a tool. Okay. Now let's move into the tool agent, which, as you can imagine, is an agent that has the capability of using tools. You pass a list of tools and it will select the proper tool, the right tool for the specific question that we're asking, and then it will run the tool to fetch the relevant details that it needs from the outside world, and then returning all this information in a natural language to you. Okay, so things that you are already familiar with. So this tool system prompt is basically the one that we explained earlier on the video. And then the tool agent consists of the following attributes. So we need to generate the Groq client, then the model that, remember that by default we are going to use the Llama 370 billion tool use. And then this is the important part. This is the tricky part of this agent. But we need to define the list of tools that we are going to use for this agent. And then this list of tools are going to be used in the run method. So the run method consists of the following steps. First of all, we expect this user message and we transform the user message into a user prompt using the OpenAI API definition. Then we are going to generate both the tool chat history and the agent chat history. And now we are going to generate the first completion. We are going to make the first call to the Groq model. And what this is going to do, these two blocks of code, is to generate basically the logic that we explained in the notebook. Let me be specific. So it's going to, first of all, return the tool call. Okay. This first call, this tool call string is basically this output. And then the parse tool call string, it's a method that mimics the same logic that we implemented in this function. Okay, so at the end, this tool call is going to be something like this. Okay, so now that we have the tool call information, we can get the tool name from this object, from the tool call. We can also get the tool by using this tool stick, because now that we have the tool name, we have also defined a dictionary that contains a relationship between the tool name and the tool. Okay, then we are going to validate the arguments. So to make sure that if the function expects a string, the LLM is not sending an integer. We want to make sure that the types that the LLM has generated in the tool call and the types expected by the Python function match. Okay. And then we are just going to run the tool with this tool run, and we are passing the arguments that we have just defined on the tool call. Remember that if we go to the tool call, remember that we had this arguments key that contains the arguments and its values to retrieve the proper information. Okay, and finally we are going to append this result to the chat history. And remember that we are adding this by using this observation prompt. Okay, so now the only thing that's missing is to make another call to the LLM in Groq, and we will receive the output. Okay, so now that we understand how all of these classes and abstractions work, I think it's going to be really cool to see everything in action. And that's what we are going to cover next. So everything is inside this section of implementing everything the good way. Of course, you have to understand that this implementation, it's not like the perfect implementation, because I'm not trying to create another framework, and I'm just trying to make something that's well implemented, but at the same time easy to understand. So yeah, just bear in mind that we are not trying to create another agentic framework in this case. Okay, so let's continue. Let's see how the tool decorator works, and instead of using some dummy function, in this case we are going to implement something more, something closer to reality, something closer to the tools that you might be wanting to implement in the future. So in this case, the function that I have implemented is a function that fetches the top N stories from Hacker News. If you don't know what Hacker News is, it's a very famous page where you have different types of stories, and many of them link to some article, another to GitHub repositories, to tweets, to whatever. And it's very, very used by a lot of people. So I thought it would be cool to have this function that allows you to retrieve a top number of these functions, of these stories, sorry. And yeah, to convert this, to transform this function into a tool. Okay, so let me show you first of all that the Python function works properly. So if we run the fetch top Hacker News stories with a top n of 5, it's going to take the top 5 stories. Let's check the first one. So too much efficiency makes everything worse. And if we go to Hacker News webpage, you will see that, yeah, that this is the first story. So everything seems to be working fine. Now let's transform this Python function into a Python tool. And we are going to do it by using this method that we covered previously. Okay, so now that we have run the tool method, the agent tool is going to be a tool. We can access the name of the tool, and we can access the function signature that, as you can see, contains all the information that we put in the system prompt at the beginning of the video. But right now the cool thing is that everything has been generated automatically. And yeah, you can see here that has a description, and the description has been retrieved from the doctrine, and we have also the parameters here. In this case, it's a very simple function, so we just need this top n argument, and it's of type integer. So everything seems to be working fine, and now let's move into the tool agent. So the tool agent, to instantiate this tool, we just need a list of tools. In this case, we are only using one tool, the agent tool. And now let's run the agent. And in this case, I wanted to check that everything works properly by doing the following strategy. So first of all, I'm going to ask the agent about something that is not related to Hacker News. So for example, tell me your name. And if everything works properly, we should see, yeah, something not related with the agent, with the tool, sorry. And as you can see, given the output, the agent has not used any kind of tool. And that's the proper way to work, because if the user message is not related to any tool, we don't want the agent to spend time on interacting with tools. But what happens if we ask the same agent about the top 5 Hacker News stories right now? So in this case, we should expect the agent to use the tool. As you can see, I have added some login to make it easier to see. But check this. So the agent is using the tool, the fetch top Hacker News stories. It's using the tool with this call dict. So this is the name and the arguments, the top n with a value of 5. And finally, is generating a result. But remember that we don't want this kind of result. I mean, if I'm asking about the 5 top stories in Hacker News right now, I'm expecting something easier to understand. And that's what we achieve if we print the output. And here we have the 5 top stories in Hacker News. The first one is that the article about too much efficiency makes everything worse that we saw in the Hacker News page. And if we click the URL attached, you can see that everything seems to be working fine. I mean, it's not like the agent redirected us to some broken URLs. I mean, the URLs are real, and it's working as expected. So yeah, this is everything I wanted to teach you about tools. My hope is that now when you start using or keep using tools from LangChain, LlamaIndex, or CrewAI, you have a deeper understanding of how these objects work under the hood. Today we are going to focus on the planning pattern, and we are going to implement a React agent using the React technique. Maybe you are familiar with the term React, but more related with front-end development because of the front-end framework. Today we are going to talk about a different React. this React stands for reason and act. And it's based on a paper that I have shared with you on the Jupyter notebook on the introduction. It's based on a paper that tries to improve the planning or the reasoning capabilities of LLMs. As I was saying, I will leave you the link here, but I don't want to get into the paper here. So what I will do is to show you a simplified version of this React agent by using this beautiful diagram. So this diagram showcases really well how the React technique works under the hood. It's basically a loop that consists of 3 different components or 3 different steps: the action step, the observation step, and the thought step. The action step is basically running a tool. It's nothing more than that. The agent decides to use a tool and it runs the tool. Then the observation step is the step in which the LLM is going to make an observation about the output of the tool. Then we have the thought step, where the agent is going to reflect on the observation that is just made. And it's going to decide what to do next. Maybe it decides to call off the iteration process, so the agent finishes the loop and it returns a response to the user, this output in here. Or maybe it decides to use another action and continue the iteration. All right, so that's basically the technique or the loop, the logic that we are going to implement today. So now let's go into as always, into the Jupyter notebook. Here you have, as always, a short introduction about the planning pattern, what the React technique is, also the link that I told you about before for the React paper, and links to the previous lessons, because many of the things that we will do today are based on the previous lessons. So if you haven't watched the videos, you haven't checked the code, I recommend you to do it, because many of the things, even some utils that I'm going to import or how we are going to create the tools, is based on the previous video. So I recommend you to take a look. All right, so let's get into the relevant imports and the Groq client. As you know, this series is based on Groq models. We are not going to use any kind of framework, no Llama index, no LangChain, no CrewAI, just Groq calls, Groq API calls. So in here, we are just going to import some typical Python libraries and also the Groq client. And we have here some utils. One of the utils is this tool decorator that we used in the previous video. Remember that this tool decorator is able to transform automatically a Python function into a tool, right? To a tool object. And this extract tag content, which is something new I created for this video, is a very similar function that the only thing that it does is to, given a text input, it's going to retrieve the content within some XML tags. Maybe it's very abstract right now, but when you see it in action, it's going to be really clear. Oh, and by the way, I'm using this Llama 3.1 70 billion parameters. In the previous video, we were using Llama 3 70 billion fine-tuned for tool use. Today, I wanted to try another Groq model, so I decided to use this one, and the results are really, really cool. All right, so let's run this cell. And let's go into some of the tricky parts of the React implementation, which is the system prompt. Okay, this is the system prompt. If you take a look, a quick glance, at first it will appear to you really similar to the tool system prompt that we implemented in the previous video, but it has some differences. For example, I'm telling the LLM to behave like, or to operate by running a loop with the following steps: thought, action, and observation, which, as you can imagine, is linked directly with this diagram. I'm telling the LLM to behave like this, to implement or to select the operations from these 3 operations: thought, action, and observation, which are the building blocks of the React technique, as we explained previously. All right, so apart from that, you can see that everything is the same. We are telling the LLM to return the tool calls enclosed by these XML tags. Also, we are defining the available tools. This is something that we are going to parse, that we are going to complete when we have all the tools defined and the function signature generated. And now the example session. This is the most important part because it's the moment when we defined the React tool, the React loop, sorry. One thing that I want you to notice is that I'm using XML tags for every message. And why am I doing this? So I discovered that the LLMs are working much better when I input this kind of structured messages. And that's the reason why I chose to make everything this way. I mean, I could do something like question, semicolon, and thought, semicolon, things like that. But I discovered that it was not as accurate. I mean, it was difficult to parse the output when I was using this kind of a structure, and it worked much better like this. And I think it's even much clearer if you want to read it. I mean, at least for me, it's much more elegant, this solution. Okay, so let's get into the loop. So first of all, we are going to ask a question, and this question is going to be enclosed by the question XML tags. Then the LLM is going to think about this question. This is like an LLM internal thought, enclosed by the thought XML tags. I need to get the current weather in Madrid. Then the LLM is going to provide a tool call. It's going to select a tool from the available tools, and it's going to provide a way to run this tool, all the arguments necessary to run this tool. In this case, it's going to use the get current weather, and the arguments are going to be location Madrid and unit Celsius. All right, then the LLM is going to be called again with this message, an observation message. Remember that this is run, the observation was the step just after the action step. And this observation, which is as well enclosed by the observation XML tags, contains the output of the tool. In this case, temperature 25 and unit Celsius. Then it outputs a response enclosed again by its specific XML tags. The current temperature in Madrid is 25 degrees Celsius. Okay, so if the agent returns a message like this response message, it means that the loop has to be finished because it has a final response. Of course, in practice, this is not going to be the case because maybe after this observation, the LLM decides after the thought process to use another action and then think again about the output of the action and use another action. I mean, the loop could be extended by any iterations as needed. But the moment that the LLM returns this response message, then it indicates that the agent is going to stop the loop. All right? And finally, I've added some additional constraints. If the user asks you something unrelated to any of the tools above, answer freely, enclosing your answer with response tags. So this is basically because suppose that I ask the LLM what's his name or to write me a poem. In this case, I don't want the LLM to run a tool for that because that's not needed. I mean, it can default to its own weights to generate a response. It's not necessary for the LLM to access the outside world with any tool. So that's basically what this constraint is doing. All right, so let's run this cell. Now we have the React system prompt in memory, and let's start the example step by step. So we are going to start by defining the tools. In this case, I chose to create 3 tools. As you will see, they are very basic tools. We have the sum 2 elements tool, which accepts 2 parameters, A and B, 2 integers, and as you can imagine, it sums the two elements. Then we have the multiply 2 elements, which, as you can imagine as well, it multiplies A and B, so nothing fancy here. And finally, the compute log, which, surprise, surprise, it also it's basically the logarithm of the input, this x, which is going to be an integer. All right, and remember one thing, that we are going to define the tools by using the tool decorator, which we defined on the previous video, and what it does is to transform the Python function into a tool object. All right. Finally, we are going to define this dictionary that relates the tool name with the tool object. And we are going to, verify that everything works by using these sum 2 elements and accessing 2 of the primary attributes of the tool. So if we run this cell, you will see that we have the tool name, some two elements, and also the tool signature, which contains the name. It also contains the description with the docstring. And this is the most important argument, the parameters, which contains the properties A of type int and B of type int as well. So everything seems to be working fine. Now let's get into the system prompt again, because we need to add the tool signature, the signature for the three tools that we have just implemented, into the React system prompt. All right, so first of all, I'm going to create this variable by concatenating in this scrappy expression the three function signatures. Let's check it, but as you can see, we have the signature for the sum two elements tool, the signature for the multiply two elements tool, and the signature for the compute log tool. All right, and now let's simply add this tool signature into the system prompt, and let's print the system prompt to see that everything is worked fine. And as you can see in the tools XML tags, we can see enclosed the three function signatures. So everything seems to be working smoothly until this point. Now we have everything ready to start implementing the React loop. And I have divided this loop in different steps to make it easier for understanding. So let's begin with the first step. The first step involves the user question. In this case, I wanted to ask the React agent this question. I want to calculate the sum of 1, 2, 3, 4 and 5, 6, 7, 8 and multiply the result by 5. Then I want to take the logarithm of this result. Okay, this is my question. So the first thing that we are going to do is to generate or create this chat history using the system prompt. That's the first message, the first prompt that we are going to add into the chat history. And then the user prompt. And remember that we are going to use all the time these tags, these XML tags. In this case, since it's the user question, we are going to use the question tag. All right, so let's create the chat history and let's run the first completion. All right, so take a look here. We have two messages. The first one is a thought message. I need to calculate the sum of two numbers and multiply the result by a specific number, and finally calculate the logarithm of the result. And then we have a tool call, which is going to call for the sum two elements tool, which seems okay. And then it's going to use this argument. So A is going to have a value of 1, 2, 3, 4, and V of 5, 6, 7, 8. So everything seems to be working fine. The LLM has chosen to use the sum two elements first, and it makes sense because if you look at my user question, I'm asking first of all to sum 1, 2, 3, 4 and 5, 6, 7, 8. So it makes sense to for the LLM to have chosen this action as the first one. Now let's add this output to the chat history as a system role type. And now let's get into the step 2. So in this second step, we are going to use the extract tag content that I mentioned previously. This extract tag content is going to take all the text enclosed by the tool call XML tags. So in this case, it's going to be basically this. All right, it's going to take this dictionary, this string dictionary. All right, and as you can see, this extract tag content, is not going to return the plain string. It's going to return a data class, so we need to access the content attribute. All right, and then inside the content attribute, we need to access the first index because it's going to provide a list, and we need to access the first element in this case. All right, so as we can see, the dictionary seems pretty good, seems fine. And now we just need to run the tool. So we are going to access the tool from the dictionary of available tools, and we are going to run this tool with these arguments. All right. And now we are going to make this assertion because I wanted to make sure that the tool result it's the same, and it needs to be exactly the same as the mathematical result that we are sure of. This assertion basically computes that, and since we are not getting any assertion error, it means that everything is working fine. And now let's add this content into the chat history. In this case, the role type is user, and remember that we need to use the observation XML tag to add this observation into the agent, because remember that just after we execute an action, the React technique is going to perform an observation on the tool output. And that's exactly what we are doing with this XML tag here. So let's add the chat history, and let's move into step 3. So now let's run this completion, and let's see what the LLM has to say. And it's going to think again about the observation that it just made. So the thought says the following: I have the result of the sum. Now I need to multiply it by 5. All right. So it's sensible. It makes absolute sense. And the tool call that it's going to use is the multiply two elements. So perfect. And the arguments are going to be 6912 as A and 5 as B. So it makes sense. It makes absolute sense. Let's add the output into the chat history with a role type of assistant. And let's move into step 4. I'm not going to get into the details of these cells because it's basically the same as we did here, okay, but for another tool. So just run this, check the tool result. This is basically the multiplication of 6912 and 5. And now let's corroborate that everything is working fine, which it does. And let's add the result into the chat history. And remember, we need to add this result as an observation XML tag. All right? All right, so let's get into step 5. Let's run the completion and let's see what the LLM has to say again. And in this case, it says that it has the result of the multiplication, but now he needs to calculate its logarithm. So perfect sense again. The tool call in this case is going to be compute log, and the arguments 34560, which is the result of the sum plus the multiplication. All right, so let's append this assistant message into the chat history, and let's get into step 6, where we are going to run the last tool of this loop. This is the logarithm after we compute the logarithm of 34560, and let's make the typical assertion to check that the mathematical computation is the same as the tool result. Now let's add the user message into the chat history. Remember, once again, I want to remind you of this over and over. We need to put the observation XML tags for everything to work smoothly and properly. Finally, we are getting into the step 7, which is going to be the final one. And if we run this, you will see a beautiful XML tag saying response, which means that the agent has decided that the loop is over. And now we can read the message. The result of the calculation is a logarithm of approximately 10.45, which is exactly the result that we got here after applying the tool result. So we have managed to make this React logic work, but as you can imagine, this is not the way to implement it like the good way, because we are not going to implement each one of the iterations from scratch and manually. We need a way to implement everything automatically. And that's exactly what I'm going to show you right now in VS Code. And then we are going to see all of that code in action in the next section. But first, let me show you how the React agent is implemented in the code base. So let's get into VS Code. Okay, so here we are in VS Code. So as we did in previous videos, you just need to go into the source folder, agentic patterns folder, and inside just click the folder related with the topic of the video. So today we are learning about the planning pattern. So simply get into the planning pattern folder, and inside click the React agent. And if you scroll down in this module, you will see some familiar things, like for example, this React system prompt. This React system prompt is basically the same that we used in the Jupyter notebook. It's exactly the same. I just copy and pasted this React system prompt to the Jupyter notebook, so there are no mysteries here. If you keep scrolling down, you will see the React agent, the proper implementation, and this is where you will see some differences with the code that we implemented in the notebook. So first of all, as attributes, we are defining the Groq client, also the model that by default, remember that we were using Llama 3.1 70 billion, a list of tools, and the tool stick that we defined also in the Jupyter notebook, but in here it's going to be an attribute, a class attribute. All right. Then we are defining as method this add tools signature. That remember that we did something very similar in the Jupyter notebook, but in this case, it's not as scrappy as the implementation that we did in the notebook. This is much more subtle, much more efficient. And then we go into the process tool calls. This is some of the core logic of both this agent and the tool agent. And let me read to you the Docker, the doc string, because it provides a really good explanation of what this method does. So it processes each tool call, it validates arguments, it executes the tools, and collects the results. And as you can see, it's not that different from what we did in the notebook, but this is like a proper implementation. And one of the key differences is this validates arguments functionality. Because in this case, we are not just running the tool and getting the results. In this case, we are also validating the input to that tool. Because we don't want to end in a scenario where a tool is expecting an integer and we are inputting a string, for example. That's something that might happen, and we want to contemplate these type of situations. All right. So, but that's basically what this method is going to do. It's just processing its tool, running its tool, and collecting all the results and returning the results with this observations variable, which, as you might imagine, it's linked to the diagram that I showed you at the beginning of the video. All right, and now we have the last method, the run method. This is a common method on the 3 agents that we have implemented so far: the reflection agent, the tool agent, and now the planning agent, the React agent, are implementing this run method. And the difference between this React agent and the previous tool agent is that in this case, we are running another loop inside the run function. And this loop, as you might imagine, is the React loop. Okay, so let's go into the different steps of this loop. But first of all, we are going to run the completion. Then we are going to check if this completion contains a response XML tag. In that case, we are going to cancel the loop. We are going to simply return the response. Because remember that the response XML tag means that the agent has decided that that's the end of the loop. It has discovered a response. It has a valuable response for us. So the loop can be canceled. Okay, if we continue, you will see this thought and this tool calls variable. The thought variable is basically the thought content, all the content enclosed by the thought tags, and the tool calls is basically the same, but for the tool call. That's exactly what we did on the Jupyter notebook. All right. So after this, we update the chat history with the completion using the assistant role, and then we print some beautiful logs with colorama using magenta in this case, and we are printing the thought. You will see this in action in a few minutes later when we run this in the Jupyter notebook, but that's basically it. I mean, we are just printing the thought. And then we are going to check if there are some tool calls in the completion. If that's the case, we are going to run the process tool calls. That is the method that I explained to you before, where we are going to run all the different tool calls that we need. And we store the result in this observations variable, and we print the results with another color, in this case blue. And these are basically the observations, if you remember the diagram, the React diagram. All right, and finally, we are going to update the chat history using user role type, and we are updating with the observations. That's the message that we are going to add into the chat history list. Okay, and that's it. Then we start again the loop and we keep iterating. So there are two things that might happen that return a value to the user. The first one is that the agent finds a response XML tag, as we already mentioned. The other one is that we get into the max rounds, into these max rounds that I defined at the beginning of the run method, that defines the maximum rounds for the React logic to iterate. And if we go beyond these max rounds, it means that the agent hasn't found any response tag on the completions. So what we are going to do is simply to return the completion of the current chat history. All right, so that's basically the logic. As you can see, it's really simple. I mean, it's just a simple loop with I don't know, 20 lines of code. But this is basically a version of the React technique. Okay, so now let me show you this in action in the Jupyter notebook with all the colors and colorama, etc. I think you're going to like it. Okay, so the first thing that we are going to do is to import the React agent, and then we are going to instantiate this React agent using the three tools. All right. And now let's run. I just copy and pasted the user message that I use here, that I created here. So let's run this and see what happens. Okay, everything seems to be going really smoothly. All right, this is really cool. So as you can see, the colors improve a lot, the readability. So we have a first thought. I need to first calculate the sum of 1, 2, 3, 4 and 5, 6, 7, 8. Then multiply the result by 5, and finally compute the logarithm of the result. Then we are going to use these tools. This is basically the action. Sum two elements. This is the tool called dict. Sum two elements and 1, 2, 3, 4, 5, 6, 7, 8. And the tool result is this one. And the observations, which is 6, 9, 1, 2. Then there's an additional thought. Now I need to multiply the result by 5. And we are using the tool multiply two elements, the tool called dig, multiply two elements, arguments, 6, 9, 1, 2, the result of the previous iteration, and 5, which is the multiplier. And the tool result is 3, 4, 5, 6, 0. All right, so the observation is basically that result. And a last thought, now I need to compute the logarithm of this result. So the LLM chooses to use, in this case, the compute log action, compute log tool, and it computes the log by using 3, 4, 5, 6, 0. That's it, the tool result of the previous iteration. And finally, we get this result, 10.45, and the observations are basically that result. So the final answer is that the sum of 1, 2, 3, 4 and 5, 6, 7, 8 is 6, 9, 1, 2. Multiplying this result by 5 gives 3, 4, 5, 6, 0, and the logarithm of the result is 10.45. And as we can see, if we scroll up, that's exactly what we achieved, the result that we got when we were running everything step by step. I hope that you are excited because you have successfully implemented the React technique, which is one of the most known techniques for reasoning, for improving the reasoning capabilities of LLMs. In fact, if you go to Llama Index, if you go to CrewAI or to LangChain, you will see that the core agents are implementing this technique. So congratulations, because you have learned how to implement a very, very important technique. And today we are going to learn about the last pattern, the fourth pattern, the multi-agent pattern. In case you are not familiar with this pattern, and in case you haven't used tools or frameworks like AutoGen, CrewAI, or even LangGraph, I will give you like a very quick summary about this pattern. But basically, what this pattern tries to achieve is to divide a task into simpler subtasks that are executed by different agents. So each agent is going to adopt a role. For example, one agent could be a software engineer, another agent could be a project manager, and another agent could be the CTO of a company. And each one of these agents are going to solve smaller tasks. Okay, so when all the smaller tasks are solved, then we can estimate, or we can say that the bigger task is going to be solved by the crew of agents, by the multi-agent application. Okay, so this is basically the approach. Remember that in the React application, in the React technique,
we have an agent that has at its disposal a lot of different tools, and it can choose between the different tools. In this case, we are going to make the agents like smaller, like dumber, and each agent is going to be assigned to a specific task. Okay, that's basically the approach. I wanted to mention CrewAI, as I was saying, because maybe you are not familiar with this framework, but I've done a couple of videos about this framework previously in the channel, so take a look if you want. And now we are going to get into the Jupyter Lab, Jupyter Notebook, as always. And yeah, I'm going to get or to explain in a bit more detail what I was saying before. So what's my approach today? What am I trying to achieve with these videos? So when I started implementing the multi-agent pattern, I was going to follow the same approach as in previous videos, like doing a very simple, a very scrappy implementation in the Jupyter Notebook, and then teaching you how to implement it the good way or the proper way in VS Code. But today I'm going to do something a bit more different, and I wanted to make something more elaborate from the beginning. Okay, that's what I've been working on, like a minimalist version of CrewAI that draws inspiration from some of the key abstractions in CrewAI, particularly the crew and the agent. Okay, we will see them in detail later, but just to let you know. And apart from that, I also wanted to draw some inspiration to borrow some ideas from Airflow's design philosophy, using the right shift and the left shift operators. By the way, if you don't know what Airflow is, it's the orchestrator, one of the most famous orchestrators, and it lets you define the dependency between the tasks using the right shift and the left shift operators. This operator right here. Okay, and in my implementation, I'm going to borrow this idea. I'm going to overload this operator, and instead of using tasks, instead of defining the dependency between different tasks, I'm going to define the dependency between agents. And instead of defining a DAG, like in Airflow, this DAG over here, we are going to define a crew, but just the same way, like defining one session in Python and defining the different agents and the dependencies between the agents inside that session, inside that crew session. Okay, right now it might be a little abstract, but you will see that it's quite simple when you see it in action. Okay, so let's get into the Jupyter Notebook. Here you have, as always, the introduction, basically what I've been saying right now. You have also links to the previous lessons, to the first lesson about the reflection pattern, the second lesson about the tool pattern, and the third lesson about the planning pattern. And now we are going to get into the first class of this mini CrewAI framework, which is the agent class. Okay, so as you can imagine, we are building a multi-agent framework, so it makes sense to create a class for the agent, for the proper agent. And as you can see, we just need to import the agent class from multi-agent pattern agent, and we can start using the agent. But let me show you the implementation first, because I want you to understand what we are doing under the hood. So we are going to go into VS Code, and I will show you how it works under the hood. Okay. Okay, so in VS Code, you will see a new folder inside the agentic patterns folder called multi-agent pattern. And inside you will see two modules, the agent and the crew. Okay, we will start with the agent and then we will see the crew implementation. So first thing I would like you to notice is related with the imports, because even if we are importing this crew object that you have not seen yet, there are two abstractions that are important here that you have already seen in this series. The first of all is the tool. Let me get into the tool that we implemented in the second lesson of this series. And the second thing that you should be already aware is the React agent that we implemented in the previous video, okay, in the third lesson of the series. Remember that we were defining all this React system prompt in the previous video, and we saw how the React technique could be implemented in very easy steps. Okay, so yeah,
this agent is going to be based both on the tool, because an agent can use multiple tools, and on the React agent, because under the hood, this agent class is going to be a React agent class. Okay? Okay, so let's get into the init method, and as arguments, we are going to pass the agent name, the backstory, and if you have worked with Crew AI previously, you should be really familiar with this naming, because it's basically the same. The backstory is like a background for the agent, and in some tasks it might help. It's very similar to the system prompt when you are dealing with a bare LLM. Then we have the task description, which is the description of the task assigned to the agent. The task expected output. This is becomes really handy when you want to define a very specific output for the task, which is the expected format or content of the task output. Then we have the tools, which is a list of tools. And remember that these are not Crew AI tools or LangChain tools or Llama Index tools. These are the tools that we defined on the second lesson of the series. Okay. And finally, we have the LLM. In this case, I chose this Groq model, Llama 3.1 70 billion versatile, and it works very well. So that's the reason why I chose it. Okay, so as attributes, well, we define the name, backstory, task description, task expected output, and the React agent. Importing the class that we talked about just before. Now, if you keep scrolling down, you will see two attributes, the dependencies and the dependents. The dependencies, I mean, if you think of a multi-agent application, multiple agents related with each other, the dependencies are basically the agents that this agent depends on. Okay, so if these agents that this agent depends on have not run successfully, then the current agent is not going to run its task. Okay? And the dependents are basically the inverse. So they are the agents that depend on this agent. So if this agent, this current agent, does not succeed, then the dependents are not going to be triggered, are not going to be run. Then you have the context, which is basically the output from a previous agent. Okay, so imagine that this agent, this current agent implemented by this class, depends on another agent. The context is going to be the output from the previous agent. Okay? And then you have this weird stuff about register agent. This will make sense when we explain the crew, but basically the crew in this micro framework is going to be treated as a session. Okay, so you define a session, and inside this session, you're going to define the different agents belonging to the crew. So what is happening here is that if we have a crew, if there is a crew active, then this method is going to register the agent to the active crew. Okay, but that's something that you don't need to bother, and you will see it in action in the Jupyter notebook. Okay, so don't bother about this because it's a bit weird, but it makes sense to use this session. Okay, this crew context, as you will see later. Okay, we keep scrolling down, and you will see a lot of shift methods, the right shift, the left shift, and related methods that basically allow you to use, let me go to this is something that we haven't seen yet, but basically allow you to use these operators, okay? The ones that we were talking at the beginning that were borrowed by Airflow philosophy and that define the dependency between the different agents. These are the right shift and also the left shift, okay? The left shift operator. But I mean, in my case, I've never used the left shift, I think, so I will stick with the right shift operator, okay? Cool. So yeah, as I was saying, all of these, the right shift, L shift, etc., are related with these right shift and left shift operators. And then we are going to also the add dependency and add dependent, which are basically ways to define this dependency between the different agents. You know, something that I think we should invest a lot of time in. You can get into the code and see how it is implemented, because it's you will see that it's really simple. And now we get into the receive context.
And this method is used for receiving context from another agent. So suppose one of the dependencies of this current agent has been successfully run, and we have an output from the previous agent. Okay, so this receive context method is going to take that output and allocate that output, that string, into the self-context attribute that we defined at the beginning of the class. Okay, here. Of course, if the agent has no dependencies, then this context will be an empty string. Okay. Then we move into the create prompt, because even if we are dealing with React agents, we need a prompt to pass to the agent. And in this case, this prompt is going to be composed of several information, but the most important one is the task description. That's something that we pass to the init method, if you recall. The task expected output, that's something that we also pass to the init method. And finally, the context. And this context, it's basically what we spoke about here in the receive context and the context attribute. Okay. Yeah, that's basically a prompt. And then we go into the main method, which is the run method, that simply creates the prompt that we have seen here with the create prompt method. And then it's going to run the React agent with this prompt, with the prompt that we have generated with the previous method. Finally, because this is not over, we need to pass this output to the dependents. That is, remember, to the agents that depend on this current agent. And that's the reason why we are going to loop through the dependents list, and we are going to call the receive context method for all the dependent agents. Okay? So that the output of this current agent is going to be allocated as the context for the dependents. Okay, I know it's a bit tricky, but when you think about it, it's quite simple, and we will see it in action with some examples, and you will see that even if the implementation might seem a bit difficult, it's really simple, and the application and the interface is really clean and easy to understand. So yeah, just wait for a couple of minutes. Okay, so yeah, we now understand how this agent behaves. And now we are going to see some examples, okay? So remember that we were going to import the agent class. We have already imported that. And now we are going to create our first agent with this new framework. The name of the agent is the poet agent. The backstory is that you are a well-known poet who enjoys creating high-quality poetry. The task description is write a poem about the meaning of life. So I was feeling philosophical when I created this demo. And the task expected output is just output the poem without any title or introductory sentences. Okay, so let's create this agent and let's run the agent. This, remember, is a React agent, but it's really simple because it has no tools. So it just, it's like an input-output prompt, basically. I mean, you give a prompt and the agent responds with the result, but without any tool involved. Okay, so in realms of existence, we wander and roam, blah, 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 searching for answers to an eternal home. So yeah, very beautiful rhyme. And let's get into something else. So we can see that this works for a very simple example, but now let's try something else with tools. Let's create an agent that has tools assigned to it. Okay, and for this we are going to import the decorator that we defined and we implemented on the second lesson of this series, the tool decorator. Remember that this works almost exactly as the tool decorator from CrewAI, from LangChain, from LlamaIndex, etc. It's basically the same. Okay. So the tool I'm going to implement is called write string to txt, and as you can see, it's a very, very complex function because it takes a string and a file name, a txt file name, and it writes the string into a file name. So yeah, incredibly complex, and we are going to define the agent. Okay. So in this case, the name is going to be writer agent. The backstory, I didn't know what to put here, to be honest. So you are a language model specialized in writing text into TXT files, so forgive me for this. It's terrible. The task description is write the string. This is a tool agent into this file, this tool agent example txt. And the task expected output is a txt file containing the given string. And we pass the tool write string to text. Okay, so let's define the agent tool example and let's run this tool. Okay, so remember, if you remember the previous video, that we had this fancy login with Colorama. We have first of all a thought, an agent thought. I need to take the given string and write it to a txt file with a specified name using this tool, so it makes sense, write string to txt, and the tool called dict is going to use this tool, write string to txt, and the arguments string data is, this is a tool agent, so yeah, and the text file name is tool agent sample txt. So it makes sense, and if we go to, yeah, here we will see this incredibly complex txt file with the string, this is a tool agent. So as you can see, our agent has successfully generated the file. Okay, so this is basically the same that we saw on the previous video. So now let's get into the dependencies, which is one of the key concepts, one of the key parts of this multi-agent pattern. So we are going to define two agents in this case: a poet agent, same as before, and a poem translator agent. This is a poem an expert translator, especially skilled in ancient Greek. The task description is that this agent has to translate a poem into ancient Greek, and the task expected output is just output the translated poem and nothing else. Okay, so let's define the two agents, and this is the cool part. Let's define the dependency. So in this case, agent 1 is a dependency for agent 2, or agent 2 is dependent of agent 1. Okay, so let's define the dependency, and now if we plot the attributes that we saw in VS Code, dependencies, dependence, dependency, dependence, we'll see that agent 1 has no dependencies. It's an empty list, but it has one dependent, the poem translator agent. And agent 2 has one dependency, the poet agent, but no dependence. Oops, sorry about that. No dependence, okay? Now, the cool thing is that if we run agent 1 now, we should expect that agent 1 output is going to be parsed as the context for agent 2, okay, as we saw on the code. So if we run agent 1, in whisper winds that gently sway, a mystery unfolds each passing day, blah, blah, blah. If now we print the context of agent 2, you will see that the poem translator agent received context is in whisper winds that gently sway, a mystery unfolds each passing day. So it's working. It's working. The context for agent 2 is the output for agent from agent 1. Sorry. Okay, so now if we run agent 2, we will expect this to use the system prompt, and remember this system prompt. And in this prompt, remember that we were passing the context. Okay, so this agent is aware of the poem generated by the previous agent. All right, so this is the translation. I don't know if you are experts in ancient Greek, but I am not. So yeah, let's suppose this is okay. But in the final example, I will be translating everything into Spanish. And since I am Spanish, I will be able to check if the translation is accurate. Okay, so yeah, let's get into the crew. The crew, remember that it's like our DAG in Airflow, our orchestrator. Okay, so let's get into VS Code again, and in this case, we are going to check the crew class. Okay, the crew class has one argument for the init method, which is a list of agents. And then it has a couple of methods, the enter method and the exit method, that are used when defining a session. By the way, if you are not aware of this session or context,
what I'm referring to when I speak about these concepts is basically this, okay? These with as keywords that let you define a context where you are creating all the agents, and all of these agents are going to be assigned with this context, okay? That's basically it. And we need all of these fancy methods, okay? I'm not going to get into details here, but you can check the code and you can modify whatever you want. But yeah, this enter and exit are for entering the context manager and exiting the context manager. And then we have this current crew attribute that we need to keep track of the active crew context, okay? And we will need that because remember that on the agent, we have this crew register agent. So the agent, if we call this, is going to be assigned to the active crew. And that's something that we are going to track by this current crew class attribute, okay? That's basically, I know it's a bit tricky, but I needed this for the interface of this framework to be easy to understand and to work with, okay? Apart from that, we also have one method, which is the add agent method that adds an agent to the agents list that we defined on the init method right here. We have this register agent that, remember that this is the agent that we were calling from the agent class that assigns or registers this agent into the crew context manager. And then this is the cool part. Maybe some of you have studied computer science or know about basic data structures and algorithms, etc. So this is a very well-known algorithm for sorting graphs. And I needed this to decide the order in which the agents are going to be run. Okay, so the agents are structured in a DAG, in a directed acyclic graph. So I needed a way to sort all of these agents, okay, and to run them without any collision in the dependencies. And that's basically what I'm doing here with this topological sort. This is something that is going to be called whenever we are going to run a crew. You will see that later on the run method. This plot is a very handy function that I will show you in detail on the Jupyter Notebook. We will see how to plot all the DAG, or the graph that we are defining with the different agents. And it's using GraphBiz, by the way. And finally, the run method. The run method, it's going to apply, as we were saying, a topological sort. And this topological sort is going to return a list of sorted agents. This agent can be run with a for loop. I mean, we can iterate of this sorted agents list, and we are not going to end up with any kind of problems with dependencies. Okay, that's basically what we need, this topological sort. And we are going to use this colorama fancy print function to make things much more easier to understand and to visualize in Jupyter Notebook. And that's it. So we will see the crew in action in Jupyter Notebook right now. All right, so first of all, let's import the crew class, okay? From multi-agent pattern, crew, import crew. And now let's create the context, the crew context with crew as crew, and we are going to define 3 agents in this case, okay? We are going to define the omnipresent poet agent. Then we are going to define a poem translator agent, which is a bit different than before because it's going to translate into Spanish. As I was saying, I'm Spanish, so we will have the chance to understand and to check if this translation is okay. And finally, we are going to get into the third agent, the writer agent, which is going to take the Spanish poem and write it into a TXT. We are going to use the tool that we defined. And there you have it, this beautiful graph-based diagram. So we have the poet agent, the poem translator agent that depends on the poet agent, and the writer agent that depends on the poem translator agent. Okay, so you can see like all the relationship in terms of context, in terms of the output of one is the input for the other one, and dependencies and dependence. Everything is condensed into this diagram at the end of the day. Okay, and I think it's much simpler to see all of these dependencies with these diagrams than to getting into the VS Code implementation and checking all the add dependencies, right shift, left shift, because it's a bit messy and difficult to understand. But if you have in mind that at the end of the day, this DAG is exactly what we are trying to implement, it makes things much simpler. Okay, so we've just arrived to the last cell of the Jupyter notebook. We are going to run the crew and see how it goes. So the first agent, the poet agent, is going to generate a poem in English. Then the translator agent is going to translate the poem into Spanish. So let's check the English poem. So in the grand tapestry of time and space, a thread of existence with displays. And yeah, in Spanish, en la gran tapicería del tiempo y el espacio, un hilo de existencia teje su lugar. So yeah, it's an accurate translation. And finally, we are going to see the last agent, the writer agent, that is going to use the writer string to text tool and write the poem in Spanish into a file. And the file is called poem.txt. Okay, so if we go to the Explorer, yeah, you will see the poem in Spanish written into the poem.txt. So this is everything for today. I hope you have enjoyed this lesson. In my opinion, this is the funniest lesson because we have put into practice all the patterns that we have learned in previous videos, the React agent, tools, etc. And it's really cool to see how all these agents can collaborate and can interact with each other to solve tasks. Of course, this is not a very complex task. I mean, it's just a sequential series of subtasks, and they are, really simple. We are just generating a poem, translating the poem, and writing the poem into a file. This is something that we could achieve with just one agent, but I think that it illustrates well how these multi-agent frameworks like CrewAI, LangGraph, or AutoGen work under the hood. So yeah, I hope you have learned something new. I hope you have enjoyed the video. As always, if you like this content, it would really support me if you click the like button or subscribe to the channel. I would really appreciate that. And yeah, this is everything for today. I hope I will see you in the next video, and until then, happy coding.